I'll start with a welcome to all the students welcome to this session on Introduction to Deep Learning for Computer Vision that Rahul will be presenting. And I'm Vivek Quatra. I'm also in Google Research, and along with Gaurav Agarwal, who's also in research, we'll be helping moderate the session as needed. So it's my pleasure and honor to introduce Rahul Sukthankar, who's a distinguished scientist and director in Google Research, where he co-leads the Perception org. He's also an adjunct research professor at CMU's Robotics Institute. Rahul has made many significant contributions to numerous areas in computer vision. And some of the problems that he has worked on like decades ago are being addressed by the leading technologies today. These include things like self-driving cars and neural networks and many others. And as the director of perception research at Google, he is at the forefront of cutting-edge research, not only in the company, but also in computer science at large. So Rahul joined Google in 2011, and I personally had the honor of working with him on a project at that time. And the project at that time that we worked on was about segmenting cats and dogs, among other things, in videos. But it was using computer vision from the pre-deep learning era. But today we'll learn how to do a much better job at solving computer vision problems using deep learning from Rahul. So take it away, Rahul.
Thank you so much, Vivek, for the generous introduction. Yeah, I have to say that when I joined Google in 2011, Vivek was one of the people who really helped me a lot, and it was wonderful to work with him closely. Right now, it's a delight to have him in my org. And yeah, thank you for organizing this summer school, and to all the folks who are taking the time to attend remotely. I know it's hard to do this in the time of COVID. So yeah, we'll do the best we can with the technology. We have the chat session, but I'm also happy to have people interrupt in the middle. So just feel free to ask questions over, over audio. I don't get a chance to kind of see the people or any hands raised, but we'll keep it super informal. It's 11:30 at night here, so you have to do your best to keep me awake as well as can. And yeah, we'll get started. As Vivek said, computer vision has gone and changed through the ages, and we are now going to talk about the kind of deep learning side of computer vision, which I think is where things are right now. I understand from people's backgrounds that that people are familiar with aspects of machine learning, linear algebra, and so on, but may not necessarily be experts in deep learning. If there are parts where I'm going too slowly, we can always speed up. And if I'm covering material that seems unfamiliar, please don't hesitate to say something in chat or just call out. I think it'll work out well that way. As with any lecture like this, I'm grateful for a lot of colleagues and friends and resources on the web who provided material that I'm using in today's talk. I've tried to be careful in terms of acknowledging figures and things that I've used throughout, but I'm really grateful to have all these good online resources. And I think today is a great time to be learning computer vision and deep learning in general, because there's so many good things to be done, including code, papers, and so on that are freely available. All right, so let's get started. So the first thing I want to do is to review kind of popular vision tasks. So when people talk about computer vision, people typically talk about some kinds of popular tasks. So let's start with an image like this. So you can see that there's a lot going on in this image. You might see that there's some people, there's a camel, there's some scenery. One task in computer vision that's quite popular is to just say image classification. Given this image, try to categorize it in one of k different categories. In this case, I might say, is this image, was it taken in, is it more like an island, a forest, a mountain, swamp, or plains? And so, there's just 5 categories, and you have to guess the answer. Now, most of you, as humans, we can, quickly say that's probably likely to be more like a mountain scene. But, how do we get there? And so I think the first part of the talk will really focus on how we get from an image to a single label. Now, something slightly more sophisticated would be to try to do image labeling. So image labeling would mean, given the same image, try to assign multiple labels, so all the labels corresponding to concepts that are present in that image. So now, in addition to something like mountain, you might have a label for camel, You might have a label for person, but on the other hand, you're unlikely to say that there's a wedding happening here or a bear. Those things are labels where you say no. So it's, instead of going from forced choice of image to K choices and picking one, you are now making a binary decision on each of a bunch of labels. But through all this, we're still talking about the image relatively in a holistic sense. The next part, of course, is to go from there and to say, for each of these concepts that you may have identified in the image, let's try to localize them. For example, where is the mountain in the image? Where's the camel? And if there are people, where are the people? And localization can take many forms. And here I'm showing something that's quite popular, known as a bounding box. So it's a little tight rectangle around the concept of interest that's saying where it's spatially located. That works quite well for objects like people, camels, and so on. It works less well for concepts that are more fuzzy. For example, if you were to say that this is a sad scene, it would be hard to localize something like that. The next generalization, so the next point along this track, of course, would be to say pixel level labeling. In other words, you've said that there's a camel here, but tell me the pixels specifically that correspond to the camel. And that task requires something that's known as dense labeling. So the labels, the number of labels in this image now, the number of labels that are required for this task is very, very high and corresponds effectively to each pixel in the scene. And so each pixel in the scene could be assigned one or many categories. That's dense labeling. One could also combine images with language. So for example, you might say, given this image, generate a caption that describes what's happening in that image. In this case, it might be something like, people in traditional dress stand near a Bactrian camel as the sun dips behind the mountains. You know, you might come up with a very different label depending on what it was. If you were familiar with the camel, maybe you might name the camel, right? That could be your, or there might be a friend in the scene. So the image captioning task is somewhat subjective, but you could also have a general version of the task. And then one can go beyond that when tasks like body part segmentation, where given a person in the scene, you might want to label that this is a lower leg, that this is the torso, this is the head, so on, and that fine level of understanding on people. And I understand from someone that one of you, at least some of you, attended Christian Smincescu's talk, and you probably got much more of a sense of ideas like this from there. But you know, we're kind of going from the most coarse grain to finer and finer grain versions. Similarly, you could try to identify 2D pose key points. So where is the wrist of this person, or where are the lips? And there, we're basically painting on top of the image. We painted a canonical skeleton that corresponds to the user that we're viewing in this image. You can also take the same concept and take it into 3D. So rather than going from an image to a 2D pose, you could actually go to a kind of 3D body and word model. And this is a slide taken from Christian, so you might have seen it in his lecture as well. One can also take a single image and try to do things like predicting the depth in the scene. Now, this is intrinsically, it's an ill-posed problem, but because people are familiar with the word, this is something that, you know, that people can do relatively well, at least in terms of relative depth ordering, and something that machines trained with the right data can also do. And this is an example from the NYU depth data set. And you can see that the pixels that are painted in red colors are in the background, and then pixels that are more blue are near the foreground. And this kind of foreground background segmentation can enable a lot of very useful effects for a lot of applications as well. So this notion of depth prediction for a single image has a lot of very interesting real world applications. Taking it to a deeper level, you can imagine doing 3D scene understanding. So that could be a variety of different tasks. You could do object detection in 3D, you could do semantic segmentation, you could do affordance prediction. So for example, given this 3D scene, where are the areas where someone can walk, someone can sit, so on. You could try to do a 3D reconstruction of the scene in terms of voxels, or you could predict things like surface normals, geometry, and so on. So there's a wide variety of things that we can do in 3D scene understanding. And I'll not get a chance to discuss many of them in detail today, but I encourage you to check them out in your when you read or see other lectures. And then, of course, Vivek mentioned autonomous navigation. Smart cars are very popular these days, and tasks that robotics or navigation require are things like how do you stay on the road? So how do you steer the car so that it stays with the road? How do you detect obstacles? So these obstacles may be dynamic obstacles. In particular, for example, there's this deer in front of the road right now. And then, of course, you want to be able to anticipate the future states of the world. So is this deer likely to move to the left? Is it likely to move to the right? And based on that, that will influence not only how we perceive the scene, but rather the actions that we take. So here, perception, cognition, and action are brought together in a real-time system. And that's one of the areas where there's a lot of progress in perception has driven the field of autonomous navigation forward. There are a number of task-specific considerations that come up as you think about the tasks I mentioned and what they mean in terms of the input and the output. So for example, given an image, if your goal is to classify the image, then of course the output might be just picking one from K. Similarly, when we talked about the various ones, yes, no labels, bounding box, and so on, you can kind of structure your network to produce different kinds of outputs. The next part, of course, is how is your training data labeled? In some cases, you can have what's known as a fully supervised training set. So someone has laboriously labeled each image or labeled each bounding box in the image, or if you're very lucky, they've labeled every pixel in the image. And of course, it gets more and more manually intensive to have very extensive detailed labels like that. So there's a whole line of work in weakly supervised learning, cross-modal learning, where you're using supervision from language or audio to do vision, and self-supervised learning. I think these areas are really interesting research areas, and we have work going on in them. But in today's lecture, we're really going to focus primarily on the fully supervised topic. But in discussion, we'll have lots of opportunities to talk about more. Then in the old days, before deep learning came back, the architecture, how do you go about this task? In the past, people used to be motivated by intuition or mathematical formulations. Now, chances are whatever you're doing in computer vision, it's probably going to be some variant of CNNs. So we'll spend a bunch of time today talking about CNNs. But ultimately, it comes down to what is in the final layer and what loss function are you using in order to get the results you want. This is probably a good time for us to kind of pause, take some questions or comments or thoughts, whether this resonates. So I'd love to hear from people in audio or in chat. Nothing? No.
I guess that was the
Hello, Rahul.
Yes, hi.
Good morning from my side. Thank you for giving this talk. So I just wanted to know how is the instance segmentation done without the CNN? Like, what are the traditional methods which we can use to instance segmentation of those balloons?
Right. So in a pre-deep learning area, how could you have done something like instance segmentation? Well, in one way might have been to say you have a very detailed model of what balloons look like. So maybe you have you've understood the physics of rubber and air pressure, and you've built a good model for balloons maybe in 3D, and then you say, given this balloon model with various parameters, how could I adjust the parameters so that I best match the silhouette of the balloon that I found, maybe using something like edge detection, right? So you could imagine doing something like that. There are a variety of other ways you could have also done it. Maybe if the parameters are small, you might have some kind of Huff transform type method to do it. But today it all comes down to CNNs.
Yeah,
Does that answer your question?
Yeah, that answers my question. Thank you.
Great.
Hey, Rahul.
Yeah.
So actually, one thing just crossed my mind while we were doing this. So in the Google Meet, so when we are doing this video transmission, you see all of your pictures are going to me. So when you were telling about key point detection, the human pose estimation, like why can't we do this thing to actually keep the bandwidth very low? So let's say I have key points of your faces, and then I know what you're speaking. Maybe let's say I can detect from your audio what you're speaking. So there are two things. Maybe one thing is just key point of your faces. Initially, I just capture one picture of your face and store it there, and then based on the key points changing, I'm changing the pictures on the other ends of the two sides. So then in that case, we don't have to transmit this whole information, and maybe like this thing just crossed my mind. I don't know. In
No,
Google
I
Meet,
think
maybe you are using this.
This is a good idea, and it comes back in various ways. There are several benefits to this to the idea. So you could imagine that rather than transmitting all the pixels, you could transmit your parameters. There are a number of people who've worked on this area. Actually, Vivek has also worked in this space. You could imagine it having several benefits. So one of it might be that you could actually make it privacy preserving, right? So you could, rather than getting all dressed up for this lecture, maybe I can just be here in my pajamas, and you can render me if you just capture my key points and render them. Another one, as you mentioned, was the media compression angle, that you can save bandwidth, and a variety of things. So but they require a specialization to the task. So maybe the same method that works in one application, may have challenges in others, and errors that you make on the key point thing, will propagate. So it's not, I think it's a good idea, but it requires work to get it to work perfectly.
I mean, yeah, it would be very difficult for a team like Google. But what I think is, when we are doing this video conferencing, your face is not much moving. Your face is still, but only you're speaking, and the background is also still. So in that scenario, so as an audience also, or as an end customer, I don't worry much about the minute changes that are happening. I just worry about the content, and your faces is appearing. So yeah, I'm enjoying that call. So in that case, maybe even with some loss, we could transmit this thing. I'm unsure Google wouldn't do this thing, but yeah.
Well, Google might actually do it. I'm not actually questioning. I think that it's a good idea, and that Google and others should do it. I think that there are very good reasons to do, variants of exactly what you're proposing. I'm actually in agreement with you.
Okay.
Yep.
Okay. Cool. Thanks.
No worries. And we can keep going, but if people have more thoughts, please chime in. So,
hello,
yeah.
Rahul. This is Shashank. Good morning.
Hey, Shashank. Good morning.
So, you had mentioned several different tasks like instance segmentation, semantic segmentation, and so on. Like, I always wondered that if I'm looking at a particular problem, let's say something like depth prediction or key point prediction, and we could think of this problem in a like multitask learning setting. So like try to do two things at once and hope that training on both helps improve the prediction or accuracy on both. So how do I know that which tasks are the most related or like would lead to the best improvements? Like it's possible that predicting semantic and instance segmentation helps a lot, but possibly even depth prediction might help. So how do I know which tasks are the most suitable for this multitask learning approach, if there's any intuition behind that?
Yeah, it's a good question, and it points to something very philosophically troubling for a lot of people around neural nets, is that a lot of your intuitions basically don't work. So you have to try a variety of these things, because so in general, yes, related tasks can help in various kinds of robustness. You might have different kinds of labeled data. So multitask learning is a powerful idea, but it's hard it's hard to do it just on the basis of human intuition alone, unless you've had a lot of experience with this data. So I don't think there's a simple answer I can give you on that. I think that's one of the reasons why deep learning is seen by many people as more something like a mix between alchemy and cooking. It's not just a field of engineering. It's hard to just know upfront and have a predictable thing. So it's a very, very empirical field, and that might change over time. But right now we're in a very empirical era.
Okay, thank you.
Right. So we're going to talk about neural nets, and I thought it'd be interesting to start with a little bit of a historical retrospective. So in particular, when I went to grad school in early 90s, 1991, so this was a car called the NavLab 1. It was at CMU, and it was an autonomous vehicle, and it was being driven by a neural network. And so that was at a time when neural nets were already driving autonomous vehicles, and it was being trained with just a few minutes of driving by a grad student who wrote this particular paper. And with just 2 or 3 minutes of driving, it would learn how to drive, and follow the road. And I thought it was amazing. And I thought that just a few years from now, we'll have autonomous cars. I decided to get my PhD in robotics, and I was wrong. The neural nets died, the field of autonomous vehicles went away. But a lot of the ideas that you see, even in papers from this time, are actually very relevant today. And it's worth looking at it and just looking at the perspective. So what's happening in this paper is that you have an input image, and look at how low res the image is. It's 30 by 32. That's because computation was not, this was with a generator in the back of the car and multiple computers, but processing a 30 by 32 image was pretty state of the art. We have a neural network, and it has 4 hidden units. Not 4 layers, 1 hidden layer with 4 units. And it has 30 output units, which each one corresponds to a steering angle. And it would take an image, and it would predict, given this image, how to turn the steering wheel so that the car should stay on the road. And if you look at it, this is the input layer, and it was before the time that convolutional neural nets had come out or popularized. So it was a flat input layer of 30 times 32 neurons, and the one hidden layer, and then this kind of output layer. But this picture is worth remembering as we talk about kind of neural nets and CNNs. So if you look at that and just turn that picture on the side, and you look at the diagrams you see in today's world, you have this input layer, you have a number of hidden units, and then you have some output layer. But now with CNNs, instead of showing all these hidden layers of the activation is just something flat, we write them and show them as these volumes or tensors. But the parallels are very useful, and it's useful for you sometimes to look back at the old papers, because you can see where some of these ideas came from, where some of the terminology came from, and also where some of the intuitions came. And you can see when it is, why ideas work and why they don't. In this particular case, a lot of the reasons were computational and in terms of data. And so this was just trying to learn during the same run that it ran on. There was no there were no data sets to train on. It was whatever the grad student could collect that day. But it's really interesting to take that perspective. So I'm going to use this diagram to help drive the intuition that we need to do CNNs. And I think that a lot of people these days, when they approach computer vision and deep learning, we tend to download code and we just try to use it. And we hear terms like ResNet and inception and so on, and we have a very cursory understanding. And I think it's worth looking a little bit deeper, no pun intended, to try to get the intuitions for what's going on in these things. And I'll try to do that in this lecture. So let's start with a CNN. What's going on at a high level? You have an input image, and the input image is typically it's 3 channels, like red, green, blue, which is why it's shown as 3 slices here. It goes through a number of things, convolutional layers, and often where the task is to do some kind of classification, there's some fully connected layer that generates this distribution over the output labels through a softmax. So input, hidden layers, and classification, and often hidden layers can be thought of in the convolutional and the fully connected side of things. I think most of you are familiar with this diagram. Many of you probably could derive the learning rules and backprop and so on. But let's actually take a look at what goes on inside the CNN. So in particular, what makes a CNN different than a regular fully connected network, one concept is this notion of local connectivity. So if you look at a neuron in one of the convolutional layers, it's not connected to every pixel in the image. It's only connected to the pixels in a specific patch. Can someone out there say why that might be a good idea? Chat, yell out. No ideas. Wow. Okay. So computationally, it's a good idea for a start. All right, so we can just say.
There was a
Yeah.
Sham on chat mentioned translational invariance.
Translational invariance. Okay, so what I described here is local connectivity. That doesn't actually give you translational invariance. The thing that gives you translation invariance is actually the next thing, which is called shared weights. And they are two related but separate concepts. So if you have just local connectivity, you could have different weights for all of them. You could still have the computational benefits of having each unit take a limited number of inputs, but you won't get translation invariance until you get the shared weights. And shared weights is making an assumption that one patch in one part of the image at the low levels of the neural net should have the same, it should be translation invariant. So if I take another patch here, for example, then you would expect the same kind of low-level features to be computed. So the combination of shared weights and local connectivity gives you this translational invariance. But that's that's a key part about CNNs. The next part is there's often a stage where there's pooling. So pooling means you go from a large height and width to a smaller height and width. And you might use something like max pooling or other things. Any ideas for why that might be useful?
You would want to reduce the height and width of the image of the input.
Yes, you're reducing the height and width of the input so the next activation layer shrank in terms of height and width. Why might that be a good thing to do?
You actually see for the firing neurons, like most important neurons. So it's kind of like activation, but in spatial resolution.
Right. So I think what I heard was that's right. If you do something like max pooling, you're preserving the ones that are firing the most, and you're also maybe your local patch now can occupy a larger space. So this same patch here versus that patch there is now occupying a greater proportional area in that image. Now, there also, what might be a disadvantage? Oh, I heard dimensionality reduction. That's another one. Making features more generalizable. Ajay, why do you think that it makes features more generalizable?
Because by pooling, you're sort of taking only the important parts of the features that you extracted. So rather than having features only specific to a single image, it might be useful for multiple similar images.
It's possible. It's a hypothesis. I mean, you could also imagine that, it might make them more brittle because you've lost a lot of information, right? Information loss it can help, but it can also come at a price. But in practice, max pooling does seem to help particularly when you're doing classification type tasks. It might not help in other cases where you want to reconstruct the precise spatial location of something possibly, right? So it does have a price. Good. So from pooling, there's also this notion of filter stride, so that the filters move, rather than going at every pixel, they can skip, and that can have computational benefits and cut down the number of weights. Another one that shows up is this is actually a piece, I think, of CNNs that often I think people have trouble understanding initially, but the notion of multiple feature maps. Can anyone say something on multiple feature maps? So rather than each filter generates one slice here, and then you have a number of filters, like 128 or 64 of them, generates multiple maps.
So like in traditional computer vision, what people do, like make filters which can detect edges or detect lines. So similar kind of features that we want to learn from these feature maps. So these kernel learn some of the particular, like maybe some are learning edges, some are learning curves, and these feature maps store that information.
Right. So one way to think about it is that you want multiple concepts to come out. So maybe you want the concept of vertical edges or horizontal edges, and each of them can be stored in this, in one of each of these different layers. And so that, you can think about it as having each of these feature maps might correspond to some low-level concept that you want. That's right. So here's a visualization of 2D convolution, and I think it's a nice animated GIF, but it also captures to me something that's going on. So really, as you put that kernel across this image, it's gathering together the information in that local neighborhood along with weights and putting it together into one feature map. I see a question. If an image has a combination of various features to an object, for example, a face, is spatial invariance achieved by CNNs? I'm slightly confused by the question. I would love a clarification.
Hello.
Yes, hi.
Actually, I was thinking that, for example, in a face, there are the features like eyes and nose and lips. So if they are haywire, then also can the CNN predict that it is a face because it has the features irrespective of where they are placed?
I see. Well, so a lot of the features that something like a CNN will get, particularly the low level, will not be something as sophisticated as an eye or a part. It will be just something like an edge, something. So the spatial invariance is really happening at that very, very low level. Now, it is true that a face has these parts arranged in a particular spatial layout. So if you just put two eyes and nose and mouth and just scrambled them, you wouldn't want that to be a face. But it turns out that neural nets, you can think about them as template matching at different scales, and it will also learn the organization of that, especially as your height and width of that image shrinks. So it really can be thought of as doing multi-scale template matching, and that's how it encodes in an implicit way the arrangement of these parts in a sophisticated concept like a face. And pooling be understood as a regularization technique, since, for example, in max pooling, you're dropping out some inputs. You can view it that way, but again, regularization typically has, yes, you can view it that way, but it's always, you can think about it as you're favoring some kinds of hypotheses over other hypotheses. I think max pooling can be viewed as dropping some of the input, but the fact that you're preserving it has kind of winner take all kind of mechanism. So if that's what you want in terms of regularization, then yes. But it's a little bit of a nuanced question. But it's one lens to view pooling, and I don't think it's the only way. Pooling can also have computational benefits, for example, right? So, and it can also be used to reduce noise, average pooling or even max pooling. All right, so let's keep moving. So for 2D convolution, the little animation I showed before applies this kernel to the input and generates kind of one pixel in this activation map, or one activation in this map. And the idea is that that same kernel is then, or multiple instances of that kernel, like 128 different variants of that kernel, are then applied in series to generate each of the things in the output layer. So it's important to realize that this kernel has the same depth as the input layer, but it only generates one feature map. And you need k copies of that kernel to generate the k feature maps that you want in the output. And I think people often get confused as to what it is that this kernel is doing. And it's really important to think about that kernel, or that filter, that's why some people call it that filter, generates one feature map. I added a slide here that just kind of talks about all the many concepts that are going on in neural nets, and it's already out of date. You have to make choices. What kind of convolutional layers you use? What kind of pooling do you use? What kind of activation functions do you use? Loss functions, regularization, optimization, and all these different things. And in general, as you become more of an expert in the field, you develop intuitions around it, or you become, you take advantage of more kind of AutoML type techniques that can do an efficient search in this space. But there are a lot of different concepts here, and I just wanted to say that we're not going to hit all of them, but some of the things that we're talking about, you can see in this diagram. All right, so one concept that I think people have had trouble with when I've talked, given these kinds of lectures to them, is the difference between a 2D convolution and what sometimes people call 3D convolutions. So let's just look at the left side of this diagram. In the left side of this diagram, you can see the picture I drew earlier, which we have the input tensor, you have the kernel, and generates one slice of that feature map. And if you do that d out number of times, you get d out the number of filter responses. So D in and D out can be different because you could have three R, G, and B coming in, and you could have 64 channels, for example, or whatever else. In a 3D convolution, what you have is that your input is now not a number of channels, it's really an X, Y, Z volumetric block. And the kernel you apply doesn't have the same depth as the input. So it's not like this one. It is something smaller, and it's translated in X, in Y, and in Z in depth. And so now applying this kernel to this thing gives you 1 pixel in this output, and then you do that by sliding this in all directions. So it sounds like 2D and 3D convolutions should be quite similar, but they're actually very, very different beasts. And I don't want people to confuse the two and develop the wrong intuitions. I'm just curious about people, in lecture. Do you have an idea of when you might use a 3D convolution?
Like if we have multiple frames and to combine the multiple frame features, we might use 3D convolution.
Yeah, and I think I saw in the chat as well, video models, medical imaging. When that third dimension is something that's spatial or potentially temporal, it has some kind of interpretation in terms of distance. Yes, then it makes sense to do it. In other words, when you want invariance in that third dimension. So if you want that same filter to do the same thing in the next frame for video or in the depth dimension in medical imaging, then 3D convolution makes sense. It doesn't make sense to apply 3D convolution when you've extracted a number of different things from a low-level set of filters, because these filters are capturing qualitatively different things and makes no sense to mash them together in that way. All right, so I think it's a...
Sir, I have a doubt.
Yeah, please go ahead.
I wanted to ask one question, like suppose if we are doing some sort of image in painting, suppose if I have a scene and I have a multi-view images of that particular scene from multiple directions. I take an image of that scene, and
Yes.
I have an image in which there is some information missing.
Yes.
Okay, so I want to input all these multi-view images to a particular CNN to get an output of an output which has the complete information of that missed information scene.
Yes.
So is it okay to use a 3D CNN in this case, because there is no temporal information there?
Right.
At the same time, I'm taking multi-view images. So is it good to use a 3D CNN, or should we go for another approach?
So I would say it's bad to use a 3D CNN in that case, because the order of the images you have, if you were to swap the order of those images, you'd still want the right output. If you shuffled those, the set of images that went in, since they were just captured randomly, a 3D CNN would not be permutation invariant. So you'd want to treat the set of images coming in some way, right? You don't want to capture the neighborhood relationship between the images you happen to order in that task. Even though ultimately you do want a 3D output.
Yeah, thanks, sir.
Good, cool. All right, so, and then of course there's the concept of a 1-by-1 convolution. And when I first came across it, it sounded like a really strange idea. Can someone say what is a 1-by-1 convolution, or why would it be useful?
To reduce the number of dimensions from
Yes.
example 4 filters to 1 filter.
Absolutely. Reducing the number of dimensions is exactly right. You want to recover the same, you want to take a block of activations of width, height, and depth, and you want to squeeze them down to, in this case, just one dimension. So dimensionality reduction is really what it's like. And if you use a number of these D-kernels, you can reduce it to some other number of dimensions. So it's taking a set of activations, a tensor of activations of one depth, and to go to a different one. And yes, you could think about it as a form of feature pooling in some ways, or a nonlinear alternative to other kinds of dimensionality techniques. And it is a weighted average. It is a weighted average along the channel axis. So it is, if there is no nonlinearity there, then it is taking a learned weighted average, data-driven. One other concept, I guess, is dilated convolutions, where you want to have big receptive fields without increasing the number of weights. And these are also known as true convolutions and other things. It's a concept that shows up quite, particularly in fully convolutional nets and so on. Can 1D be used for text input? Yes. Yes, there are ways of processing text with 1D convolutional neural nets. There are also other techniques that have become very popular lately, things like transformers. So those are worth checking out. All right, I'm going to, let's see, so I'm going to speed up a little bit about some of these things. So in addition to the kind of regular convolution, there's also a notion of separable convolutions. So here, for computational reasons, you may choose, rather than having this big block that's kind of a dense block for each output feature, you can actually have limited connectivity in depth and create these kind of depth-wise separable convolutions. They're very popular in the literature. And there's also this notion of a grouped convolution that shows up. And the grouped convolution is a slightly weirder concept, but it's related, where you have one, you actually break this computation into two pieces. You have one kernel that processes one part of the output vector and another kernel that's responsible for the other part. And this part, group convolutions, for most people, they were unfamiliar with it until they saw the AlexNet paper. And the AlexNet paper, they actually have these two different pieces with group convolutions. So just as a question for anyone who's read the AlexNet paper, can someone say why group convolutions were used?
I have not read the paper, but according to me, I feel it is less computationally intensive.
Absolutely, that's right. They wanted to fit it in two GPUs, and they kind of set it up that way. So that's your intuition is absolutely right. Great, good. So going from AlexNet, you start seeing architectures like Inception, and in Inception, you see interesting things happening in these blocks. So I just want to take a look at one of these Inception blocks and see what's going on inside it. And the concept in the first version of Inception was that a layer would go through, a 1x1 convolution, a 3x3 convolution, a 5x5 convolution, and some max pooling. And really, they were saying that we don't know precisely what to do at each layer, but we'll try all the different things and then, concatenate the filters together. And when they refined it in the paper, you can see that they ended up putting 1x1 convolutions like this to do exactly what some people said before, which is to do dimensionality reduction, so that the number of filters you get in the next layer doesn't explode. But it's worth seeing some of the intuitions. I know we have limited time, lots to cover, but I just wanted to run you through Inception on my way to something like ResNets. So ResNets are now still a relatively popular architecture to use, particularly for these kind of classification problems. And the idea here is that they have these skip connections that are happening. Skip connections, the concept of skip connections is, dates back into the 80s. But what's interesting about ResNet is the way they formulate those skip connections. So skip connection doesn't just take the input and skip a number of layers, but it actually copies that input over, and then other computation happens, and then they add it together. So they're not concatenated, they add it together. Can someone provide me an intuition as to why this might be an interesting or good thing to do?
Can I answer this question?
Please.
Yeah, one thing is the reuse of the features, and the second thing is to solve the vanishing gradient problem,
Good.
which we experience in
right.
players.
So good. So on the vanishing gradient problem, what is the vanishing gradient problem, and why does this ameliorate it?
So when we use the backpropagation thing to update the weights, as the convolutional neural network gets deeper and deeper, and when we backpropagate, when we go towards the weights present near the input layers, the gradient becomes zero. So it goes back to zero. So it's not possible to update the weights then. So to solve that particular problem, the reuse of features is a good idea.
Mm-hmm. And so it's not just reuse the features, but there's actually a shorter path from the output back to the input through these connections. So you can actually pass the error back with a smaller number of hops. But yeah, these are absolutely the right intuitions, and they enabled us to go and train much deeper networks. And so it was skip connections, but it was also the idea. The second intuition, I think, which is worth capturing, is that in many ways what you're saying is that what you want here is something very similar to what you had back there, but just with some delta that's added, that residual piece. And so this is one way of getting there. So it's saying that it's mostly what you already had a few layers back, but then this part is responsible only for finding that shift between these two. Good. So we're kind of at this point, we've discussed what goes into a kind of state-of-the-art CNN for image.
Rahul, I think there's a question from Shivansh.
Oh, okay.
Sorry to interrupt.
Yeah, please go ahead.
Actually, I was just wondering if the problem was just the vanishing gradient, like we do regularization in weights, right? We keep them. So the regularization is like lambda into weights squared. So can't we have this thing? If the problem was just the vanishing gradient, can't we have this inverse of that regularization? Like let's say I'm 1 upon mod of, or you can say modulus of weights, and that's squared, or the gradients like this thing in initial layers. Like to solve this problem by using these skip connections, can't we have something more simple or basic, like adding some loss when the weights of the gradients are less?
Yeah, so people have tried with various kinds of intuition, but the question is, will it do the right thing for you in the sense that, if for example, if you magnify the errors, it goes back through the network, right? Could it actually amplify noise? So that's a very common question. So when the signal to noise ratio gets less, just kind of adding a scaling thing won't be enough. So I'm not saying it can't be addressed through regularization. With the right regularization, you can do a lot of things, but this does have one benefit, which is cutting down the number of hops. You can also say that in the residual framework, really it's about saying that you've already basically solved the problem at some point, and really it's about refining that solution more and more, and that's the kind of residual intuition. You can also address vanishing gradient by putting intermediate heads to kind of feed error, into the middle of the network. People have done that. Inception did that in a variety of places. These kind of side heads, auxiliary heads, and then you remove them at inference time.
Hi, Rahul. I had a question.
Yeah.
So, could you please discuss some of the cons of group convolution? For example, recently, I don't think group convolutions is used extensively directly. I think most of it is used in the form of combination of depthwise and pointwise separable convolutions. Can you discuss why group convolutions or the cons of group convolutions used individually? Because in a way, it's sort of giving us sparser connections, which might be helpful not just as a regularizer, but also maybe just just like, for example, as a regularizer. So
yeah, no, I think it's a good question. I mean, in many ways, some people, you could just view group convolution as a computational hack. And so if you don't have those limitations anymore, it's one more complexity in your system. You've got these parallel paths and you have to kind of put them back together. Depthwise convolutions feel kind of simpler to discuss and do. And, many people would rather do that rather than, go through the additional complexity of creating. If you do group convolution, how many groups you're going to have? Like, it adds a number of hyper, parameters and decisions.
Exactly. That was my next question. Can you, what is the sort of trade-off when you're looking for let's say 2 or 64 groups in group convolutions? How significant is that trade-off?
Right, and so I think it really is an empirical one. And in those cases, I mean, sometimes you're up against a computational barrier, right? You can't fit any more in this particular GPU or whatever. And there it makes sense to explore ways. But hopefully, if you're in a less constrained environment, then people typically would rather make their decisions elsewhere. Group convolutions tends to fall towards the bottom of people's area to play with, because really you are constraining your CNN in that particular layer. And I think for people aesthetically also, it just doesn't feel like a great thing to be doing.
Thank you so much.
Thanks. Yep, no worries. So we are now moving from whole image classification to localization, and particular object detection. So I'm going to try to hit the highlights of this part. So historically, it was a little bit of a mental shift for people. How do you get a CNN to do a good job in object detection? So I do also want to, for people who may not be familiar, the difference between detection and segmentation. Segmentation, again, is really to draw the boundary around the object, and detection is, about putting a bounding box. So we're going to focus on the one on the left, detection. So one way to do detection, very intuitive, is to, if you have a whole image classifier, is to take a box and say, is there a camel here? How about here? Just slide it everywhere and just ask the same question. And people have done that in the pre-deep learning days. They did it, and then of course people redid it in the deep learning era. This creates, this is computationally of course expensive because you're looking at all these different bounding boxes. Most of them have very little chance of being interesting or useful, and it's a very unbalanced problem because the probability of a box containing a camel is going to be 1 in a million maybe, rather than being a balanced choice. So it's a hard. It's one approach, but it's not a great approach. A more promising one is to have some method that tries to guess which might be promising bounding boxes, and then only apply your neural net to those ones. And when object detection was becoming popular, people often used pre-deep learning techniques, objectness, and many other things to try to identify these windows. And it was called selective search, and then you'd verify with the neural net. So the idea was you'd get an input image, and RCNN did this. So input image, you extract about 2,000 region proposals, and then on each one of them, you apply your CNN to classify each region. The question then is, of course, couldn't a neural net do this part itself? And the answer is yes, you could. And so the idea there was that one neural net would look at the image and simultaneously try to have an output that was a class label as well as parameters for a bounding box. And the idea was to learn from labeled data both of these at the same time. So what you're trying to do is simultaneously learn the concept that's in this box as well as the location of this box. Now, how to learn the concept, we've already discussed. It's nothing different than doing the whole image classification. But learning how to kind of find the right size and shape of this box is a little bit of an interesting idea. And I'll give you the intuition for it. So imagine that the ground truth for this, you're detecting stop signs, and the green box here is the ground truth, and your neural net guesses this red box. What is the error that you should give the neural net? How well did it do? And in this particular case, they found that if you use something like the intersection over union, how many pixels are in common between the hypothesis and the ground truth versus the union, that's a signal. Now notice the signal is scalar. It's not saying, the ground truth is not saying you need to shift the box to the left and up. It's simply saying you got an 80%. The neural net has to then figure out how to adjust its weights so that that bounding box becomes tighter around the object. And so, but this has been very effective and it's done the right thing. And so more state-of-the-art approaches like faster RCNNs do exactly that. They're convolutional layers, feature maps, and do all this. I had a slide here about kind of how you can do convolution using matrix operations, but we are not going to bother with it. You should know that this is done, and this is how convolutions become effective, efficient, and that's why they fit well with graphics hardware. I did want to draw a contrast between the kind of classic CNNs, which is kind of convolution, fully connected, and give the output like a cat, versus a fully convolutional layer, a network that gives you something like dense segmentation. Quickly, I'd love to hear from someone. Can you tell me one benefit of a fully convolutional net?
I think it helps in the training because the number of parameters in the fully connected network becomes a lot in number.
It could be. What about in the set of, like, look at this input image. It's a 227 by 227 image. Going in here, and out comes this thing. What is the size of the input image and the output image in a fully convolutional one?
It's the same. So I guess, yeah, I guess maybe when you want to create something like an image which have a local context neighborhood and a neighborhood kind of relations exists, then you can use convolutions to generate, because then the hypothesis would be true.
You can use, that's when to use convolutions as an input, but if you want to do dense labeling as an output, then a fully convolutional net has a nice property that you can use on any sized image.
Any size image, yes.
Right, fully connected one has the notion of a rigid input size, but a fully convolutional one has the same number of weights no matter what your image size. And so that's an interesting property. Good. From fully convolutional neural nets, a very popular idea has been this notion of a U-net. And so U-net starts with a big input image, it scales it down, gets deeper and deeper and deeper, and then it upsamples it on the other path, but it also has the skip connections that go for the detailed part. So it has a kind of coarse-defined piece. You see a lot of these in dense prediction type of networks, and it's worthwhile if you're doing those kinds of tasks to become familiar with it, the details of it and the intuitions behind that. I think it's a pretty nice architecture and captures, it avoids the information loss that you could have, and also addresses some of the vanishing gradients, through skip connections in a different way. And you could even have a residual net type interpretation of this, which is pretty nice. And so that gives you this kind of notion, and that gives you a variety of different applications. So you can use these networks to do things like segmentation, colorization, super resolution, and so on. And I included a case study for something you can download from our group, which can do real-time kind of dense prediction and give you these body parts. And it's done as a fully convolutional net, where you can effectively have different feature maps repeated to do body segmentation on each of these parts. So you can check that out. You can use very similar ideas also to go from a black and white or grayscale image to a color image. And there, what's something nice about this task in terms of training data? What do you think? Do you have to pay people a lot of money on Mechanical Turk to get this data?
We can take images from the internet and just convert them to black and white.
Exactly. And someone said it's self-supervised. That's right. So in other words, you don't need additional, that's right. You can take a task and use the input data in itself as a self-supervision signal, and that's really attractive. And it's also really attractive in helping you get the intuitions for self-supervision for for future research as you try to go beyond fully supervised nets. All right. So one thing to remember is that any differentiable function can be used as a loss function, even in another neural net, which is what you see in things like GANs. But often when you're doing neural nets, it's worth thinking about what is my problem type, what do I have in the last activation, and what are the loss functions. So it's not a complete random search. There are good intuitions to develop here, and it's good to understand what are the pros and cons of these various things. And there are a lot of good papers that you can read, as well as blog posts that help you develop these intuitions. There are a lot of topics we didn't cover today, right? We didn't talk about video, which I really am excited about. Vivek's also keen on that. We didn't talk that much about things like robotics or computational photography. There's a lot of things going on there, and a lot of stuff in the machine learning space we didn't discuss, but it's good work that's happening. In the last couple of minutes, I just wanted to show some areas where there's a lot of active research. So one is, how do you do neural nets for 3D content, and even representing that 3D content, whether it's point clouds or volumes or surfaces. We don't have the right answers for all of this, because there's pros and cons to these different representation methods. And similarly, how do you do convolution on these 3D volumes? Should you do them on surfaces or volumes and various different things? I think there's a lot of interesting research happening when you treat neighborhoods as graphs versus surfaces and volumes. So if you're interested in these areas, there's a lot of rich exploration to be done. So to end precisely on time, in conclusion, we have, so this was an introductory lecture. We focused on computer vision using fully supervised deep learning. We tried to cover a lot of the key concepts behind neural nets and their extensions. And I do want to remind people that neural nets will always try to cheat you. They'll always try to find the easiest way out of your problem, something that you never wanted or expected, but it was easy for the neural net. So you have to work really hard to make sure the neural net also works hard. And so often you may just give up on a problem because you didn't choose the right loss function or something trivial like that. And it is very much an experimental discipline at this point. We covered a number of applications, starting from image classification, worked our way through object detection, semantic segmentation, and some things on human body parts and so on, and ended with a quick look at deep learning for 3D. A lot of topics I didn't cover, and we might be able to cover some of these in the discussion we have coming up, are things like, what do you do when you don't have fully labeled data for your task? So it says self-supervised, weakly supervised learning. There's also increasing excitement around using simulated data, for example. We didn't talk about video at all, and that's an area which I think is really interesting. Multimodal perception. If you have the same neural net ideas working in images, you can pretty much apply similar ideas to audio. So why not use multimodal input at the same time? I think deep learning provides us with this great opportunity, yet many of us, particularly those of our researchers who came from backgrounds where they only looked at images or only looked at text or only looked at audio, I think they're at a disadvantage. I think students such as yourselves have an opportunity to view this all as one unified thing and really make significant advances in joint representations, joint embeddings, many, many cool things that can be done in multimodal side of things. And then, of course, pairing perception with action around ideas like robotics, I think is another area of interest. And there you have to have perception that's happening under significant resource constraints. You can have perception happening with data constraints. You can have perception happening with different kinds of input. So I think the space is rich. I think we just kind of scratched the surface here. But I think it's a good place to end the lecture. And thank you very much for keeping me awake and staying active. Let's take some questions.
Rahul, should we take the scheduled 2-3 minutes pause so that people can stretch, have a bio break?
Yes.
Quick one? Okay.
Let's do it. What do you want? 3-minute break?
Sure, yeah.
3-minute break. See you in 3 minutes. I'm going to give people a minute or two. Time to restart.
Hi, Rahul. I had a question.
Sure.
My question is regarding multimodal perception. So basically, when you take a multimodal input, let's say a video and an audio clip, internally the two representations are completely different, right? So when you sort of aggregate them later on, how can you discuss, or can you just elaborate on how you might consider the representations being two completely different spaces while aggregating? And how do you?
Yeah, it's a good question. Let's actually try to make the problem a little bit more specific. Let's try to say you're taking a video that contains both images, a sequence of frames, as well as an audio channel, and your task is to do the same thing we did in most of this lecture, which was to say, trying to classify it, right? You might want to say, which of 10 classes is it? Is this someone driving a car versus playing soccer or something like that? And so you could imagine that there could be image features as well as audio features that helps you distinguish between these classes. So the simplest way to do multimodal features is to really treat the two inputs as relatively independent towers. So you might say you take the audio side and you turn it to something like spectrograms. And so spectrogram would be almost like an image. And then the image side, of course, is a sequence of images. So you could have either spatiotemporal CNNs or a sequence of image level CNNs and average pool them together, and then do something on the spectrogram side, and then put everything together into some kind of fully connected layer and train that end to end. So that would be one relatively straightforward way to do multimodal audiovisual classification.
No, my question was let's say in the first stream or in the first modality, I have images or a stack of frames which are real world images. And in my second modality, I have a spectrogram. So the representations of the two internally are sort of different, right?
Yes.
And it's not exactly intuitive to sort of aggregate them directly.
No, we're not actually asking you to aggregate them directly. We're not saying, let's make a big image consisting of a real world image with a spectrogram pasted to the bottom part.
No, but at some stage in the network, we would want to sort of combine the features learned, right?
Right, you would, but you could say that deeper in the network, if each of them were encoded down to a fixed dimensional vector, let's say 100 or 1000 dimensional vector, 1024 dimensional vector for the image side, and the same for the audio side, you could then imagine concatenating those vectors, which you can think of as being points in some high dimensional embedding, and then you could say stacking them together makes sense.
Okay.
So in other words, what we said implicitly is that let's come up with some kind of embedding for the image side and the audio side, and stack them together, and and then come up with a classification at the end.
Right.
There could be a variety of different things to be done, but that's one way. It's relatively simple to at least imagine. What else?
Hi.
Yes,
Thank you
hi.
for an amazing talk. So in your recent paper, Speech to Action, you have predicted the action labels from speech. So do you think actions can be generated maybe from speech and some taking consideration of some extra information?
Sorry, so well, I'm glad you enjoyed the speech to action paper. That's actually, a lot of that work was done by Arsha, who will be joining us soon, and I don't know if you had a chance to meet with her in the panel discussion. So your question is whether you could use speech to generate an action.
Actions, yeah.
And what did you mean by generating actions?
Action frames, generating the videos from speech.
Oh, I see. Yes. So that would be a model that can really, right. So that is an interesting grand channel, which is to say, if you just have a transcript or you just have an audio channel, can you actually go all the way to generating a video? And people are trying these things, and we haven't seen great results yet, but I think that is a very worthwhile goal. You could imagine if you're looking at text and images, you'd like to be able to say, given this image or this video, what is a textual representation? And given this textual representation, can you generate me a visualization of that text? And right, there could be many visualizations, there could be many-to-many mapping, but it would still be a very exciting and worthwhile task to do. And you could imagine that being done. I would love to see more work in that space.
Okay. And another question was, you talked about 3D, especially the point cloud representation. So as we know that point clouds are irregular and unstructured, so how do you think convolutions can be applied on them? Like how to consider the local information because they are unstructured and unordered as well?
Yes, great question. And let me see if I can take us back to some of the slides and credit Tom Funkaza for this. So you could imagine if you get something like a point cloud, you can do things from that point cloud. So you can define neighborhoods in that point cloud in other ways. You could, for example, do some kind of nearest neighbor graphs on them, or you could look at things within a specific radius, a variety of different things. And then that defines a neighborhood rather than them being just a collection of unordered points. So
first thing would be to define the neighborhood.
That's at least being one approach. You could imagine, I don't want to rule out that there could be methods that'll just ingest this point cloud, in arbitrary order, and then implicitly generate all that and do it end to end. But right now, most people approach it by coming up with a more explicit representation to feed to the net.
Okay, thanks.
You could imagine that this itself, learning graph, that is something that the net could do, but then it would have to remember what was in the point cloud and then learn the concept of what a neighborhood is. It's not out of the question that could be done end to end, but right now most people don't do that.
Okay.
What else?
Hi, Rahul. Thanks for the great talk. My question was about active perception, which is where the scene is not fixed and instead you can focus on certain parts of the scene that may be useful. I was wondering if the attention mechanisms that are commonly nowadays used in language models might be applied here, or if this is a good use case for such kinds of models.
Yeah, active perception is an area that's I've been interested in for a long time, and I wasn't interested about that area even as a grad student. One of the things that makes the problem interesting is that you're actually taking a hard decision, right? You're saying, I am here given this information. What's the next sequence I take? You could imagine using. People have approached it with reinforcement learning type techniques. People, can also apply attention and other things. It's hard to evaluating these active perception systems sometimes is tricky, in the same way that robotics tasks are easy because are tricky because it's now no longer doesn't fit the traditional paradigm that we have these days that's so popular, which is saying, here's your training set, here's your validation set, here's your test set, because now you've actually created a sequential loop. So maybe the question should be, given that you have the chance to explore this environment for some period of time, and then you're going to get tested on some other task, maybe then you could then tease the difference between two different active perception systems and say which one did a better job.
I see. The second part of my question was if the attention mechanisms that are used in language models and also have been recently incorporated into some computer vision models, do you see active perception as a good use case for such kinds of mechanisms?
So I think the devil is in the details there, right? So the attention, in many ways, an attention mechanism is simply a way of assigning a weight to your input. And so, some people see a connection between that or something like saliency, but really it comes down to what will you do? How will you then use that attention? Will you simply make a myopic decision and go towards the area that has the highest attention, but that could cause you to just reinforce the areas that you're already familiar with? Are you instead going to try to explore areas of the space that you were not attending to? How do you want to actually try to get information about the scene?
Sort of like, I've seen something like this being applied in reinforcement learning where attention has been used to explore areas of the environment that haven't been explored enough yet. So I was wondering if, say you have a scene and you don't have great features from certain parts of the scene. If you could use some penalization based on attention to focus more on those parts of the scene.
I think that attention would be an ingredient in how you get there, but it's not going to be like simply saying you will use attention won't. It's still a very ill-specified problem because it's hard for the neural net to know that it's doing poorly. Like, how does it know that it's got bad features in that area in the absence of supervision that's strong? How will it realize that? And if so, how will it know to attend to this part versus some other part of the scene if it's trying to go to the less explored regions, right? So there has to be some way of trading off between this kind of, in the same way that RL has to deal with this explore trade-off, the same will have to happen here.
Right. Thank you.
Yep. I see a question on chat. It says, so instead of using 3D convnets, can we apply convolutions in 2D and fuse the feature maps of consecutive frames? Another way for action recognition using CNNs could be to separate representation to spatial and temporal variations and train individual CNNs for each of them and combine their outputs. Can you please talk about this? So yes, so 3D convnets are not necessarily an obvious thing to do for video. It's entirely possible that you can apply frame level features and then do some kind of temporal understanding over it. You could imagine using an RNN or an LSTM on those. I've seen people have, there's been a lot of work done in those areas. So I wouldn't necessarily say that 3D convnets are even the dominant way of approaching it. I think that there's still a lot, depending on what exactly the task is that you're trying to do for video. I think you need different things. Open to hearing thoughts around that. I do see another question's also asking, 2D networks are quite common in action recognition now. Yes, I think 2D networks are common and have been in the past as well. There's a lot of benefits to 2D networks because you can train them also on images, whereas the 3D ones can only be trained in video.
Hi, I had another question. My question was related to how do you think modern computer vision architectures are sort of lacking or lacking behind human perception? For example, let's say recently there was a cognitive experiment in which they showed that if you give a human very fine level cues, let's say very simplistic images such as a simple edge, just a simple edges or a simple outline of a fish with some very minor cues, let's say the fins being of a particular different type, very, very fine cues. Humans can sort of recognize or understand or pay attention to that and learn from that very quickly, but sort of computer vision architectures miserably failed on that sort of setting. So where do you think our recent or modern CNN architectures are lacking in terms of that?
So one could arguably say that the task that you're describing there is more of an abstraction task, right? So it's saying that humans seem to share this kind of abstract representation in terms of line drawings and many other things. And in humans, it can also be that often that comes through a lot of cultural work. So people are trained, people draw stick figures and say, these are people. But stick figures and people don't look anything at all similar. I mean, they are very, very different concepts. Yet for humans, because they're being culturally trained, they map to somewhere similar. I think the types of systems we're using to do perception with computers right now are really inadequate to try to tackle the kinds of tasks where the representation, where the input signals are so different in the kind of low-level features.
Thank you.
Yep. See another question in a couple of questions in chat. One is, do you see a time in the future where we can use a general model architecture for use for both language processing and image tasks, with all the overplay that's happening right now, what sort of architecture do you think that can resemble? I do think I want to see a general architecture that's useful for both language processing and image tasks, but I don't, I guess I don't want to make a bet for what that could be. I mean, it'd be very easy for me to say, oh, some kind of transformer, because that's hot right now. But, you know, let me resist that. I would like to say that we haven't really had as many people as should be looking at image and language together, and really looking at joint representations. I think it's a really interesting area, and I think we've, you know, barely scratched the surface there. So I don't think my opinion is going to be sufficiently informed for it to be useful. I'd rather, you know, people try it out, and we'll come back and look at this in a year, hopefully get with some better results. There's another question in chat saying, we have intuitions regarding representations learned by CNNs that they go from edges to shapes to objects and so on. Do the same interpretable intuitions hold for really deep networks as well? If so, what's the difference in representations learned by shallow and deep networks? I think I don't agree with the premise. I don't think the intuitions, I think people are really good at hallucinating what they want out of the data they see. I don't think CNNs necessarily are going from edges to shapes to objects. They're doing something that's kind of a complicated form of template matching, distance metric learning, and implicit representations. And we like to see patterns in them that correspond to representations we've used in the past. So I think deep networks just have more opportunities to build really, you know, I guess they have opportunities to stack these nonlinearities, compose their lower level features. And it happens to be the case that you can train deep networks well on data, but then you can distill that into a shallower network. So I don't think there is an intrinsic difference in representation between them necessarily. It's just the deep networks, given the kinds of training paradigms we have and the data we have and the amount of data we have and the supervision we have, tend to train well and generalize well. And then you can transfer some of that to shallow networks. I don't know that I agree with the representation side on the intuitions.
Hello, Rahul.
Happy to have a disagreement with people on that, though, if there's someone who wants to argue the opposite side. Hey.
Yeah. So actually, when you showed us about UNet, the autoencoder decoder, I was wondering basically what an autoencoder decoder is a dimensionality reduction, right? Sort of like an PC or maybe dimensionality reduction. Now, what happens, the hypothesis when we do dimensionality reduction is when we decrease the input size to a latent representation, and we have the decoder which kind of decodes from that small latent representation to the final input. This is the setting. Now, in the UNet, we have the skip connections. So you see, when we are encoding the image down, we are also passing the information to the decoder side. So the decoder is not just using the latent representation, but also information from the encoding part. So shouldn't this violate the hypothesis of dimensional reduction, or let's say autoencoder decoder?
So I don't like, so I'm just going to give my personal opinion, right? So I don't think autoencoders are a good way to learn representations. And the UNet, I don't think, is doing an autoencoder. What it's really doing is it has a dense input and it's a dense output, and it's doing a mapping between a fully supervised mapping between that dense input and dense output in an architecture that's coarse defined. So really it's saying that I'm going to do spatial pooling in some sense to get down this path and to have combined features that are spatially distant into what you might call latent representation, or I might just say happens to be a very, very small image with a lot of depth. And then expanding that out. And the skip connections are a way to do the deltas from that coarse representation back out. So unlike an autoencoder, the image and the output are not the same. They're actually two different things of the same dimensionality in height and width, at least.
So
I say that an autoencoder, the features that an autoencoder learns might be useful, but they could be totally useless as well.
Okay. So like what I was thinking was maybe in UNet, what we could do is just simply convolutions without reducing the size of width and height of the the tensor block that you're having. Just convolutions with keeping those width and height same and changing the channels along the channel dimension. I think it could, like theoretically, it should do the work that UNet is doing. Do you agree?
No, I disagree. I disagree with you. I think that this is an interesting point, right? So what you need, in some sense, it's like what you're showing here, right? But you need your convolutions in some sense to possibly get a bigger. I mean, you need to have it possibly get some longer range dependencies. Now, for some tasks, maybe for things like colorization, you could imagine it could be done with a very local thing. You may not need a scene level or kind of broader thing, but I think for many tasks, you may actually benefit from having kind of longer range connections. Now, there's a limit to what you can do with that and fully convolutional nets, but fully convolutional, even with kind of dilated convolutions, does give you bigger kind of spatial receptivity, right?
Hello, Rahul.
Hey.
So I wanted to ask a question about ReLU activation functions. So like most of our normalization and regularization makes data zero-centered. So like some values will be negative and some value will be positive. So like why do ReLU performs very good in practice when it kills many of the neurons, as many of them are negative?
Yeah, it's a good question. In the past, people avoided activations, right? So people use sigmoids and CAN-H and so on. Like it says that you didn't want information loss happening there. But it turns out that so ReLUs drop information, but there's a bias unit. So it need not necessarily be half of your activation gets lost, but it does drop information. The point is you are training with backprop and you're training end to end. So if that information was valuable and the net did poorly, then it is incentivized to try to keep it in the next iteration. So the belief with the ReLU is that yes, you will lose information through that nonlinearity, but hopefully it's information you didn't need to solve that specific task on which you're being penalized through the loss function.
And another question regarding like when to use max pooling or 1D convolution. So like in 1D convolution, we are not actually losing any features, but in max pooling we are. So like, don't you think like using 1D convolution to decrease the depth of the feature maps and then using bigger kernel size or combining the feature maps into lower dimension is a good idea?
Right. So max pooling, I mean, there's a philosophical point. So most architectures that use max pooling tend to do it in the context of something like a classification task, where you might just at the end need to say whether or not this image has a cat. And so you could argue that the amount of information that was in the image initially, you don't need to preserve all of that. So information loss is totally okay. A 1D convolution, you mean like a 1x1 convolution, right? So a 1x1 convolution will do dimensionality reduction. And you could say that in a 1D in that 1x1 convolution, you're kind of squishing it all together. There's no actual loss of info, but depending on your loss function, it may or may not be the case that losing information, losing information may in fact be precisely what you want to do. And max pooling has its proponents. If your goal is to really retain only the most important aspects, then max pooling seems like a reasonable thing to do.
Okay. Thank you.
But max pooling, I mean, for what it's worth, I think max pooling is less popular these days than it used to be in the past, because people have found these other alternatives, and also because people are doing more dense output type tasks where you do benefit from keeping that information around. And so architectures like UNet, right, they don't have max pooling in them. Actually, they do have max pooling here in this path, but then they recover it from the other channel.
Yes. Okay. Thank you.
Yep.
Hello.
Great. Hey.
Hi, Rahul. So I have seen UNet being used in a lot of biomedical applications. So is there something specific to UNet that makes it special for such kind of application?
I don't think that there's anything specific about UNet that's tied well to biomedical applications, but biomedical applications often have a dense prediction type of task, right? So maybe you, in biomedical applications, you're asked to segment out a tumor or things like that. Like you actually want pixel level outputs. And so if you need pixel level outputs, then UNets are a natural choice.
Okay. And another question, like is there some application like where we can try pooling across the depth of the feature map?
So you're saying, can you do pooling over depth rather than over a spatial neighborhood, right?
Yeah.
Yeah, people have done. It is possible to do things like that.
So
and
in which scenarios, like, is it can be used or it is used? Like,
so that would be exactly the kind of case where I think the previous person, when they asked the question, they asked about using a one-by-one convolution in depth. That would be a one-by-one convolution in depth versus using max pooling. So max pooling will just give you one output, but a one-by-one convolution depth might give you kind of k-valued outputs, right? So often in depth, you don't want to go all the way from, say, 128 channels to 1. It does seem like a very drastic reduction. That's why people tend to use one-by-one convolutions there instead, because then they can go down to some, more manageable, but not such an extreme value.
Okay. Thanks a lot.
Whereas if you think about where max pooling has worked, it's done over like a 2x2 neighborhood. So it's really 4 values going to 1 value, not like 128 values going to 1.
Sure.
Yep. What else? I see there's a thing on chat. So in recent years, we've seen a huge decrease in error on ImageNet dataset, even got better than human error. I'm concerned we have solved the dataset, but not the intrinsic task of image classification. The deep learning models fails on natural images where a human can outperform very easily. Can you talk more on it and give insight for future design of our problems that is more focused on solving the intrinsic task? Okay, it's a good question that brings a lot of different things in there. Let's take a moment to say, what is ImageNet? So ImageNet is a set of images that were collected by photographers under particular conditions and categorized particular way. So an image that appears in the ImageNet dataset is different than an image that a robot might kind of collect in the wild. It might be similar to what a human might collect in the wild with a camera when they frame a particular object and they're trying to create something. So ImageNet at its heart has an assumption that some intelligent agent took that photo with some purpose in mind. And usually it was to share with friends or as a memory and so on. On that task, there's again the choice of what the output labels are. And ImageNet has a particular set of output labels. And it has lots of dogs, for example, but it has very few instances of other things. Anytime you have a data set is going to introduce a bias into your problem. And we just have to be aware of the bias. It has been a good point that progress in ImageNet, treating it as a proxy task, has been useful. So if you have 3 architectures and they perform in a particular rank order in ImageNet, often those have also worked well on other tasks. And that has been why ImageNet has been successful, not because the ImageNet task has itself been valuable or the actual numbers on ImageNet are valuable. I don't think the comparison between ImageNet and people, tells you anything deep. It just happens to, be that ImageNet used as a proxy task has learned representations that have worked well in other cases. One could say that in real intrinsic tasks, the notion of time is really important. ImageNet doesn't have that. Maybe you might say that in a real robotic perception task, what really matters is how you steer your vision system as in active perception. ImageNet won't help you there. So I think ImageNet has played an important role in the history of our field, particularly with deep learning, and we should recognize it and celebrate it for that. But we shouldn't imagine that it will help us solve the task that we need in the future.
You mentioned ImageNet not having a notion of time. I didn't quite understand what you meant by that.
By time? Yeah, so ImageNet is saying that ImageNet is a set of, it's a very sparse sampling of the world where someone magically created an image with an object that's largely centered in that image. How did that happen? It happened because a person took that photo, right? So in tasks where people take photos of that sort, then ImageNet task is a good proxy. But if your goal is to train just on ImageNet and then apply it to other tasks, you may encounter images that don't look at all like what ImageNet has in its training set.
But ImageNet, like generally, you would be using ImageNet as a pre-training step, right? So eventually, the sort of examples that you would be encountering on during evaluation would be sort of in distribution to the images that you are fine-tuning your model, which is pre-trained with ImageNet on. So
right. So
that
what does it
make a difference, right?
Right. So what does it mean to pre-train ImageNet? It's saying that ImageNet is capturing something valuable about the probability distributions of low-level features typically, right? You're not necessarily going to say more than that. So in that sense, it's been really valuable. And in fact, ImageNet is generalized in ways that we would never imagine, to things like medical imaging and so on, because the low-level features that you learn from ImageNet do tend to be useful. But that doesn't mean that the absolute numbers you get on ImageNet necessarily correspond to how well machines are doing versus humans are doing on a particular task.
Right.
Yep.
Hi. Just had a question about, okay, so you were talking about segmentation and object detection, which are basically doing, okay, segmentation is at least doing a pixel level classification based on which pixel belongs to what object. But these kind of methods don't really learn an abstract representation of an object. Like they don't understand the object as such. So say in a video, if there is an object in the frame and in the next frame it gets deformed or something, then it's hard for the current systems to understand that the object that was there in the previous frame has been deformed to form the object in the next frame. So do you think there are some good ways to capture such relationship between pixels belonging to an object, or capture the nature of the object itself, like probably like graphs or something?
I mean, I think that it's an interesting question. I mean, in your question itself, you asked about this. You can pose it as an understanding. I mean, it's arguable to know the level to which something that can do a segmentation is doing any kind of understanding at all. I mean, what it's learned is in this typically fully supervised task, it's learned how to go and associate and pixels to objects, but in the poses and so on that it knew well. It's not necessarily the case that it has any deeper understanding of this being an object at all. It's simply doing a pixel labeling. So it's not surprising from that standpoint that it will do poorly on kind of a very deformed version of that object if it's never seen it in that sense in the training set. You could imagine one way to approach it, though, is if you have good access to synthetic training data where you have understanding of how these objects deform. If you have models of that and can render videos of them deforming, you could imagine training better semantic segmentation systems that are not only looking at space, but also kind of space and time together and get better results. So this might be an area where synthetic training data helps you without necessarily even doing anything particularly radical on the neural net architecture side. It could be a data problem, not an architecture problem.
Even if you have a data set like that where there is a supervised relationship between an object and the deformed version of itself, you're sort of still learning only the mapping that this object when deformed becomes something else. So I was wondering, my question was more towards so like say the deformation is something like compression where the outer part of the image moves a little bit into the image or into the object. So I was wondering if there is any way to capture that movement through some sort of representation.
It might be, but it's tricky because I think even for humans, when we talk about these things, I think we're making a number of kind of philosophical assumptions, right? We're saying often we're dealing with objects that have rigid parts or they preserve volume. It's very hard for people to say that a cloud is the same cloud as it's changing its shape. Like there, our intuitions break down as well. And for a neural net, it's not coming in with any of these preconceived notions. So it's trying to do the best it can in terms of just segmentation. It doesn't have an explicit representation necessarily saying these things. Now, when researchers are dealing with people, for example, they are deformable objects with specific properties, like you can't grow an extra arm. And so the representation that that researchers use in order to understand people tend to have these explicit characteristics in them. They have skeletons with fixed number of limbs and so on, and they perform really well even under weird poses and so on when trained right. That's different than saying that, and that's a kind of class-specific version of it. But you could imagine what you're trying to say, if I understand correctly, is saying, can you encode these intuitions we have about objects in general in better ways? And I don't think architectures will get you there. I think either you'll have to have explicit representations or the right kind of data to drive the implicit representations into the directions you need.
Right. Okay. Thank you.
Yep. There's an interesting general question on the chat. So the general question is, what are some qualities we should develop to become a good researcher? What, according to you, is key to perform excellent research? It's a hard question, and my perspective is only going to be one perspective, so you should talk to other people on this. I think that as a researcher, you have to be persistent. You're going to experience failure all the time. And in general, many of the good ideas you have only seem good to you. They may not actually be supported by experiments, and they may not actually be good ideas at all. That doesn't mean you should stop being a researcher. It must mean you have to have more ideas. You should talk to more people. You should do things. So I think being persistent is important, because if you get discouraged by your initial failures, you're going to attribute that to something in you rather than realizing it's just part of the process of being a researcher. So I think you want to be in a situation where you can express your intellectual curiosity, where you can have colleagues who are comfortable with your failure and with discussions where you can talk about failures. If you're in an environment where everyone's expecting to succeed all the time, you're going to be tempted to really either not take risks or to falsify your results so that they match what you want intuitively. And you may do that on a subconscious level, and it's not going to make you a great researcher. So you need to find the balance between a challenging environment and an environment that's sufficiently safe, where you can try these experiments and not have them impact your career or your thing. And it's hard. So it's not just what you have to do, but it's the environment that you're in.
Rahul, I don't know if you addressed the question on 3D deep learning. Did you already answer that?
No, I did not. Let's actually go up there. I see that. You mentioned graphs can be used for 3D deep learning. Can you elaborate on that? Let's actually go to that slide. And I was simply talking about it in the sense of graphs are one way of expressing neighborhoods per point. So I think someone in an earlier point had asked the notion of, if you have an unordered collection of points, you could imagine building a graph of the k-nearest neighbors of those points. And then that graph encodes some useful spatial relationships about the distribution of those points and can help build the right representation you need for 3D deep learning. And people have said, yes, the use of graph neural networks has been restricted to areas where explicit structures, such as social networks, chemical interaction. What's your opinion on their use and task where explicit structure is absent, such as activity detection and image captioning? So I've collaborated on work that has used graph neural nets for activity detection. And in particular, we used it to identify relationships between people and objects they were interacting with. So there was you could imagine there being a graph created by a node representing each actor in the scene, and another node corresponding to objects in the scene, and linking the bilateral links between objects and people. And you can actually use graph neural nets in that scheme to do quite well to understand, who's interacting with which object. So I think that it is possible to use graph convolutional nets in such domains.
Hi Rahul, I had another question. So let's say if I stylize a part of my image. So let's say if I stylize or let's say put a filter across the left side of all the images in my data. And if I use, let's say, any common CNN architecture, do you think it would still be able to perform as well? Or a better way to reframe the question would be, do you think these networks focus more on the structural or syntactical knowledge or information, or rather on channel-wise knowledge or information?
Let me just rephrase your question to make sure that I answer the right one. You're saying that if I had an image and I transformed, let's say, the left half of that image with some filter, will a pre-trained CNN that I have that's already working well on something like ImageNet, will it be robust to that filter? Is that right?
Yeah.
Rather than training, right? Because if your question is different, which is saying that if you take all of ImageNet training and test and replace the left half of the filter with it, will it work well? So one thing that if you affect the left half of the image this way, you're basically breaking the notion of spatial invariance in your CNN. You're saying that you've applied the filter to only half of the image, the other half doesn't have it. So something inherently, you've given the neural net a really nasty kick. Right. It may still be able to recover from that, but you've effectively violated one of its core beliefs or assumptions. More generally, I don't think that it's responding to any kind of structure. It actually is representing it. It's understanding the clever. It's cheating to the best of it can. So it's exploiting all the little low-level nuances it can in that image. And so applying a filter to most images, unless they've experienced that in their training set, I wouldn't necessarily expect representations to be robust to them. Now, it could be that the filter you apply happens to be a filter that's common to other things, like maybe a blurring type filter or an intensity filter that shows up as variations in the training set, in which case your net may happen to be robust to it, but there's nothing intrinsically about the neural net that would make it robust to such things.
Right. Thank you.
Yep.
Hi Rahul, my question is about self-supervised learning. So like how should we choose the proxy task for our main task? Like does using a rotation make sense for key point detection? Or is it more like experimentation that try different proxy tasks and which works better for you? Go with that.
I mean, self-supervised learning is a very active area of work, and different people come at it from different angles. I mean, one task that did work quite well for people, for example, is this notion of colorization. That was a form of self-supervised learning, very easy, that kind of does some stuff, but it doesn't. You have to realize that the kinds of proxy tasks you do will influence the representations you learn down the line. Personally, I like the idea of using naturally occurring things as self-supervision. So for example, if I can use cross-modal learning to do self-supervision, that's that's attractive to me. I'm less of a fan of trying to guess tasks, proxy tasks that when I apply them will get the right representation, because it feels like I'm now just doing feature engineering, but in an indirect way, and trying to convince myself that I'm doing self-supervised learning, when really I'm injecting a lot of my own intuitions into the task. Now, it may still be worthwhile for me to do it from an engineering standpoint, because I may not have the funds to collect the data that I need for the fully supervised version. It may still be a valuable thing to do, but I don't know that this kind of manually exploring the space of proxy tasks is the best use of time in self-supervised learning.
I see. Can you talk about what is cross-modal learning? I didn't caught that.
So by cross-modal learning, I I mean, I think it's not as common as, as I would like it to be down the line, but you could imagine, let's say you have inputs coming on multiple channels, audio and visual. Could you use one to supervise the other? Similarly, I mean, people, when they use speech captions that are temporally localized with a video, I would consider that a use of cross-modal learning.
Okay. Thank you.
In addition to the point Yash made, don't you think that a more general pretext task like sort of predicting the correct sequence between frames should work generally for most cases? Because ideally you're not sort of learning a particular spatial understanding of your data. For example, in the case of rotation, you might be sort of looking at certain rotation or spatial cues there, but in a more general example that I gave regarding a sequence prediction, you're sort of learning images as a whole, and it should work generally, right?
I mean, it's a great hypothesis. In many ways, it connects back to what Vivek and I were working initially. We had a project called Couch Potato that was looking at lots of data that was coming. The question was, what could you learn if you just watched a lot of YouTube data? Could you actually learn what you needed? Could you build the right representations from it? And I can argue on either side of the question. One side would be, I mean, models for doing sequence-based learning have been really popular and have worked really well in natural language. So things like GPT-3, if you think about it, are doing a sequence prediction task. It's different in video because you don't, you have you don't have the same building blocks that you need for sequence learning in video as you have in natural language. You also don't have the same constraints on grammar, language models that you have. And you can imagine that a video has a lot of very nuanced, different features that you could imagine that are very, very different representations in the actual signal space. So I think while it's attractive to say, we'd like to be able to just watch video and learn awesome representations, I don't think there's enough experimental evidence to show that that's happening right now. I mean, it's still something that I am interested in. I just don't have great ideas right now on how to do it.
Thank you.
One could also take the roboticist's viewpoint, which is that if you don't have the ability to take action in that space, maybe your representation is already going to be, constrained. Maybe it is important to have the ability to take actions, because then you can explore counterfactuals. So maybe this was one evolution of video, but if you try taking some different action, maybe it would evolve in a different way. Maybe the notion of having an embodied agent with a tight action perception loop, maybe that helps you build better representations. There are people who argue that that's certainly the case in biological systems. So it could be that that's needed.
There's a question on chat. Yeah.
On chat, yeah. What is the intuition between upsampling? What does it mean to go from less features to more features? Okay, yeah, that's a good one. Let's actually go back to the UNet slide to talk about that. So upsampling, one way to think about it is that, yes, you did add data, but you still use the same lower dimensional representation you had in the previous layer to create that. So the upsampling, it's not that you created information per se. I mean, you did, because it's a combination of the activations and whatever was implicitly encoded in the network as it went up that layer. But often what happens when you upsample, you also integrate in UNet type architectures, you integrate a path that's not only going through the upsampling, but is also incorporating data from the same level up. Now there's pure upsampling. For example, if you're learning things like a super resolution task, right? So there, the hope is that the network has implicitly learned characteristics about the world such that when it upsamples and it's doing this ill-posed problem, it's going to be biased towards directions that happen to correspond to the statistics of real-world scenes. And so that's what the hope is in upsampling in that front. So at the lowest level of upsampling, you're going from, you're simply increasing the dimensionality but you're using a latent dimension, you're using a latent space that had fewer dimensions. In the case of kind of true upsampling for something like super resolution, you're then saying that you're constraining that to be more connected to what real world statistics are like in an implicit manner. I hope that answers the question. All right, and again on chat, continuing the thread on self-supervised learning, why have unsupervised contrastive learning methods which just compare represented image with an augmented image significantly outperform methods performing pretext tasks, like colorizations, rotations, etc.? Yeah, this is a good question, and I think that a lot of it also comes down to how these tasks work. So if you treat something like colorization or rotation, there is really no relationship between data instances. You're saying here's an image, and this is that transform versus that image. Something like contrastive learning, on the other hand, is developing relationships across data points, and so it may not be a completely fair comparison. Is what I'm saying, and I actually do view those methods as not being. I mean, I guess the proxy task that I would consider that's more unsupervised would be a reconstruction task where you just have an autoencoder that's reconstructing that image. We know those don't do that great. So we know self-supervised methods do better than just an image reconstruction through a bottleneck. And so I think that contrastive learning is fundamentally different from that. We're running out of time. With a minute left, maybe just take a last one or two questions.
Rahul, it's very, very late for you.
It is.
I really appreciate what you've done. So maybe you could just leave the students with one parting thought, some words of advice.
Oh wow, that's very deep. It's 1:30 in the morning, and I don't know that I can impart great wisdom. I think not giving up is important. But you don't want to repeat the same mistakes. You want to, try making conscious decisions and search your complex space effectively. But it can feel very disheartening at times. As a researcher, you will experience failure a lot of times, and often the failure is for reasons beyond your control. You can often use that to kind of create a sense of bitterness and cynicism, but that doesn't really help you down the line as a researcher. So it's hard to find that balance between being grounded in the real world and appreciating the failure as training signals, but then not, giving up from it.
And I might add another hallmark is spirit of giving back, which we have just seen. Rahul, you demonstrate that. Thank you so much.
Absolutely. Thank you so much. Yeah, I think that's absolutely right. I fully agree with Manish. I mean, you should really view this as, helping your colleagues and to treat the relationships you have with other researchers much more equally. Don't, exploit the people who work in your team and try to suck up to your superiors. That's not a good recipe for life. Thanks again. It was great to have you. Great to meet all of you. Thank you for organizing, Manish and Vivek, Gaurav, Ashwin, Rahul. It was great to have this chance. Sorry I couldn't be there in person, but pandemic.
Thank you.
Thank you, Rahul. That's great talk.
Future. Bye.
Thanks a lot, Rahul.
Thank you. Thanks a lot. Thanks.
Thank you, Rahul.
Thank you.